For humans, we often view our world as a small number of sophisticated objects and events, rather than as individual pixels or particles. Why do we do this? And what is the mechanism behind it? So this is going to be a quick sketch on why and how to capture objects as a part of intelligence. This isn't going to be super polished, but will just be something quick that I can reference. So, to make correct decisions, we often need to take into account past history. Specifically, we often tackle problems where at each time step, we'll receive some input observations, and we need to make some target-output decisions or predictions. Initially, our task is easy, as we'll only have to take our current observations into account to make decisions optimally. But as we proceed further and further, there will be more and more history that we'll have to memorize and take into account if we want to make decisions optimally, which will become an increasingly infeasible task to achieve. So instead, what might be good to do is to reduce history to only a hopefully small amount that matters, and focus only on that. So in this previous example, instead of memorizing and processing all of past history, we would like to memorize and process only the smaller amount of actually relevant points. In computer science and other fields, compacting history into a smaller amount of data is often known as capturing the state of a problem. My argument is that what we humans perceive to be objects or events are mechanically collections of related state. They are state that show up or become relevant together, then go through transformations together. But let's look at some details. So before even getting to objects, let's first talk about identifying points in history that matter, which will be a prerequisite to capturing state and objects. So what we're going to do is to learn the relation between a target decision and all of its previous history, using a neural network. Now, there are many relations that our neural network cannot learn perfectly, especially as we're going to try to go fast with small, shallow networks, but this will still let us hopefully roughly measure how much each input, or in other words, each point in history, contributes to the final outcome. Again, this won't be perfect, as even beyond the use of neural networks, the inputs will likely be significantly correlated. But we don't need this to be perfect, as what we're going to try to do next is to repeatedly pick various small combinations of relatively impactful points, and try to see how effective they are by themselves. For example, let's say we suspect that these 4 points might be particularly impactful. We'll learn a new neural network to measure how well they enable the target decision to be made by themselves. But perhaps we also think these 3 other points might be good instead, so we're going to try to do the same with them. After trying many combinations, we'll choose a combination that is particularly effective while involving a relatively small number of points, and proceed to the following. Then, we'll form state from the points in history we selected. Specifically, we're going to check if the points can be condensed into an even smaller amount of data we'll have to memorize. So let's say we've selected these 3 points. We'll try to see if we can learn a sequence of relations, specifically small neural networks, that look like the following. At the first relevant time step, we'll learn a relation that transforms the selected points into the initial state. Then at each following relevant time step, we'll learn additional relations that take in the selected points and the current state as input and modify the state further. Finally, when it comes time to deciding the output, we'll learn one final relation that determines the output based on the current state we've arrived at from the previous steps. If this sequence of relations can be successfully learned, then that means that we can further compress our points down to just this single state to keep track of while solving this problem. Otherwise, then at each relevant time step, we can simply only memorize an increasing amount of state and process it all at the end. One good way to look at this is that if points can be merged, then we're looking at transformations of an object. Otherwise, we're looking at its further categorization. For example, let's say we're currently tracking a group of state that we've decided collectively represent, say, a car. If at our first relevant time step, we see that the car has moved, this doesn't represent a significant increase in the amount of information we have to track. So all we have to do is to update what we are already tracking. Similarly, if we see that the car has changed directions or the door of the car is opened, this may all be information that we can capture within our existing state. So all we might have to do is to update it instead of adding more. And on the other hand, let's say at the first relevant time step, we saw enough to lead us to memorize a group of state that we've decided collectively represent, say, an animal. But on the next relevant time step, we see new information that lets us further categorize what we saw as, say, a dog. This is additional information that doesn't fit into the state we previously had, so we'll track this as additional state. And perhaps on the next time step, we get even further information that lets us classify what we saw as a husky. So that's information that will require even more states to save. Next, it's not the case that a particular state will be relevant for all problem instances. It might be that sometimes an object will be present, and we'll want to memorize and process that state accordingly, but other times the object won't be there, and instead, we don't want to bother with the state at all. So what we'll try to do is to divide problem instances based on what state is relevant to them, and treat different problem instances differently. This will let us become even more efficient at what we memorize and process, and will also let us begin building more sophistication. Specifically, it's the case that for an input in a relation, it might have changing correlation with the final output, which we can capture with the nonlinearities in our neural network. For certain problem instances, an input may be strongly correlated with the final output, while for other problem instances, the input may not be correlated at all. So what we're going to do is to save instances that have high correlation versus instances that don't separately, and try to learn a new relation that distinguishes between them, similar to the process for checkpointing and creating solutions. If a relation can be successfully learned, then that enables us to treat different instances of a problem differently, where we can capture and process state in one branch while completely ignoring it in the other. And again, like when creating solutions, we can keep branching more and more to better handle even more scenarios, while preventing the amount of state tracked in any one scenario from becoming overwhelming. And we can then add increasing sophistication, such as, for example, adding branch merges, where we may decide to stop tracking a particular state by remerging branches if we run into a scenario where the object disappears or is no longer relevant. And we can look for loops, which will enable us to greatly simplify our structures by treating different time steps instead identically, in the same uniform way. Finally, through the previous process, we gained the ability to capture and handle different objects differently along different branches. But now, it might be that some of these objects are not entirely different, but can be considered as variations of the same object. For example, a red car versus a blue car, a car appearing on our left versus a car appearing on our right, or perhaps even more complex variations. And we can instead capture these variations as combined, more generalized objects. For example, let's say we have these two branches capturing two different objects and decision-making tied to them. What we'll try to do is to learn a transformation, or in other words, a function, from the output of one object to the output of the other. If this can be successfully learned, then we can combine these into one branch representing a single object, but we will also have our transformation and additional state capturing which variation of the object we have. Objects can also exist in continuous variations. For example, they can exist in a continuous range of sizes, be in a continuous range of positions, etc. And like with continuous generalization when creating solutions, we can capture a continuous transformation between the continuous variations of an object. To find these continuous variations, we'll use the same discrete and continuous methods as in continuous generalization, which I won't detail here. But if successful, we can capture a range of variations using a single branch, a single state, and a continuous transformation. So if, for example, we see that the object is, say, in the 0.0 state, then we can use the transformation to effectively handle this case as a 0.0 branch. And if we see that the object is in the 0.3 state, then we can correspondingly handle this as a 0.3 branch. And this can lead us to recognizing objects in states we previously haven't recognized before, such as the 0.1 state, allowing us to appropriately handle situations we couldn't have accurately handled before. But anyways, like how we build increasingly sophisticated algorithms when creating solutions, through these methods, we'll be able to develop increasingly sophisticated ways of capturing objects, of capturing the world, enabling us to tackle truly lengthy problems. My argument is that this matches our human need and ability to view our world as smaller collections of objects and events. But again, Like with creating solutions, there's much that needs to be proven empirically, so there's much engineering work ahead, and time will tell.